you guys about this morning is the IMTA system as a concept, and kind of try to work in exactly where the sea vegetables fit into the IMTA as a whole. So on the tour, I'll be talking about the system as a whole, showing you the system design, where the animals fit into the system. And then Megan will be showing you the sea vegetable components, and Dennis is going to be showing you the macroalgae seaweed components. Just remember though that all of those are connected within one system, sharing all the same water. It's constantly recirculating. First though, I want to talk about aquaculture a little bit. I'm a fish guy. I can relate to him. I like to have fun. I can relate to him. So let's try to have some fun today, but seriously talk about aquaculture. Why do we need aquaculture? There's a lot of controversy around aquaculture. People are in the general public, which would be you and me, are really starting to embrace the concept of aquaculture as society moves from a hunter-gatherer type of concept more to the farming agrarian kind of concept that we have with all of our other food products. Right now in the United States, we import about $17 billion worth of aquaculture products. It's about 65 to 85, depending on which group you listen to, for the percentage of all the seafood consumed in the United States. We export about 4.3 billion, so we have pretty good exports, but we still maintain a deficit of about $10 billion, half of which is shrimp. The U.S. population is growing. Currently, we're at 330 million. We're adding one person every 31 seconds to our population. I just checked these statistics two days ago to make sure they were right. There's like a clock that changes constantly that you can log on to. It's really interesting. It's really scary. But all those new people are going to require food. So to maintain food security in our country, we need that, and also in the world. The world is growing by 2.3 people every second, and we're approaching 8 billion people in the world. So we need food to feed the people, because we love people, right? So we need the food to feed them. Currently, nutritionists want us Americans to double our consumption of seafood, because seafood fundamentally is healthy. It's a very good source of low-fat proteins, et cetera, and vitamins and minerals, particularly once we incorporate our sea vegetables. And oftentimes, commercial fishers will say, well, we can fish more, we can get more fish. Fundamentally, that's not true. The oceans are pretty much producing all the fish that they're capable of. So here's a graph that shows you the growth of fisheries, including aquaculture in the world since the 1950s. So post-World War II, we saw expansion of the industry, growth of technology, et cetera, and we saw the steady growth of aquaculture. There was a scientist, I think at the time he was at Hui or Woods Hole, and he did some predictions of how much, his name was John Ryther, he did some predictions of how much productivity the ocean could sustain back in the 1970s. So on that graph, look at the 1970s, and he predicted approximately when and how much within about 12% of the actual number, and almost predicted the date based on the current growth at that time. And you see in the late 1980s a leveling of productivity from the oceans. So that's based on the primary productivity, the phytoplankton, et cetera, which convert the sun energy to the food that all the rest of the food web in the ocean can use for the productivity of the fishes that we harvest. Aquaculture is filling the gap in demand. So aquaculture does not compete with commercial fisheries. It provides the filling of the gap for demand. So And if we're going to have seafood, we're going to continue to demand seafood. That gap needs to be filled, and fundamentally, it's not going to come from the oceans. It's got to come from aquaculture. So this is the reason we're seeing this movement from this hunter-gatherer to farming type of concept with our seafood products. So that just sets the stage for why we need aquaculture. We could go into discourse on that for hours and hours and hours, of course, but those are some of the fundamental concepts. I want to talk now about the systems and what types of systems. When we think about aquaculture, most people think about open ocean systems, cages, and that sort of thing. But most of aquaculture is actually done in ponds. And now we have improving technology that's allowing us to move to onshore recirculating systems, which are very high efficiency systems. So, and our IMTA concept, our IMTA system is a land-based onshore recirculating system. So I'm going to give you the basics of recirculating design. Now, there are people in the room, this is old hat for them, but there's many people in this room that probably have never seen this information before. So I'm going to go through it to bring all the boats up, right? So we start with a tank that has our fish in it. That's what we need to grow our fish. We feed the fish. The fish produce feces and urine. And we have to filter that if we're going to reuse this water, because those things become toxic and will kill the fish or crop, which is something that we do not want to have. So the first step is generally solids filtration, removing the solids from the system, followed by what we call biofiltration. The current technology primarily uses biofiltration, which is taking advantage of natural bacteria that are in the world everywhere. They're in the soils, they're everywhere. We call these nitrifying bacteria. They convert the nitrogenous waste in the urine of the animals into less toxic forms of nitrogen. It's not non-toxic, it's just much less toxic than what is originally excreted by the animals. So going from ammonia to nitrate. So and in the middle there's a step where it's converted to nitrite before it goes to nitrate. But ultimately, as plant people, you know that ammonia and nitrate are very good fertilizer, right? The other thing is that fish don't particularly well process phosphorus, so there's a lot of phosphorus produced in these systems as well. But that can be managed a lot with better feeds, et cetera. In the concept of IMTA, we don't need to use those technologies because we want the phosphorus anyway. And then fundamentally, when you're done, that water's clean, it can go back to the animals and be reused. So this cycle can be done over and over and over and over and over again, as long as you're managing the buildup of nitrates within the systems. There is a need for makeup water. The standard nowadays is 5% makeup per day, or up to 10% for a system. And when I started working in recirculating systems, 10% was the standard. So the standard has gotten better as technology has been produced. And then I'll show you what our current numbers are for our IMTA system in a bit. You have loss of water through evaporation, cleaning, getting rid of the waste. You have this concentrated solid waste that comes out of your solids filtration that you have to have something, have to do something with. So the basic recirculating technology has some limitations. Those are, you have waste produced, right? Those wastes have to be treated before the water that you do discharge from the system is discharged. You can't be a polluter if you're going to be a good husbander, right? This process is much easier in land-based systems because you have complete control of where the wastes go. It comes through a pipe. You have complete control of where those wastes go, and you have complete control of the processing of those wastes. With water use, nobody's ever achieved 100% recirculation because you do have this need for water to remove the waste and that sort of thing. And then you also have loss due to evaporation. And as you're moving waste away from the system, this discharge, you have loss of water. So you don't have, getting 100% recirculating is the goal. It's a goal that probably will not be met, but we want to get closer and closer and closer and closer to that goal if possible from a water use perspective. There's many perspectives on recirculating: energy use, water use, efficient feed use, moving those nutrients around and reusing those nutrients. But we have this waste. What are we going to do with this waste? The primary wastes are the uneaten feeds and other solids, the feces that's produced by the animals. And then we have the liquid wastes, the urine that's produced by the animals, that we have to deal with in the system. One characteristic of all these wastes is they're very high in nutrients. All right, there's a lot of nitrogen, a lot of phosphorus, some, minerals, etc. So those of you who are familiar with aquaponics, etc., understand this. But one of the fundamental differences in aquaponics, freshwater aquaponics, and the IMTA that we're talking about is the fact that we are not only growing fish and a plant, we're also growing many other species. And I'll go through a list of different species that we've been working with and that have possibilities in the system. And the idea now is to look at these wastes, right, and use them differently. When we first started working with this concept, though, we ran against a little bit of a public perception problem. When we talked about using feces to feed from the fish to feed another animal, we got the comments in public forums like this: you think I'm going to pay good money to eat that, something that's been fed that? So we had this public perception problem. We did some engineering technology to remove that problem from our system. So all of our wastes now go through a fermentation process, which fundamentally converts it from feces into a biofloc, which is a bacterial colony. There's other critters in there as well as the bacterial colony. And that fundamentally solved that problem and allowed us to really stabilize the solid waste in the system. So what that helps us do then is we are turning what were previously thought of as waste now into resources. So we don't think about anything in the system as a waste. Anytime we see something that we think is a waste, we want to reframe that and how do we use that as a resource to produce some other animal or plant or whatnot in the system. So that's the basic philosophy of the integrated multi-trophic system. No waste. Everything's a resource. How do we use those resources either within the system itself as a recirculating concept, outside of that system, or whatnot? We just want to use them as resources. The concept comes from open ocean aquaculture, where they're really struggling with their waste problem. And what they're doing is they're using ocean currents. They'll have their sea cages. Underneath the sea cages, they're doing sea cucumbers, sea urchins and whatnot, which are eating the settleable solids, the fine solids, and any phytoplankton that grow. They're trapping with mussels and growing a second crop with mussels, or a third crop with mussels. And then the theory is that the fine solids have been removed and the water passes through kelp is one of the standards, and they're producing sugar kelps as a plant product. So you can see when we think about the concept of integrated multi-trophic systems, the multi-trophic is relating the concept of where you draw your energy from in the ecosystem. So the fish draw their energy from the feed, the mussels draw their energy from the particulates and the algae, and the sugar kelp is drawing their energy from the sun, and then getting nutrients then from the rest of the system. And the concept then is that you have mitigated a portion at least of the waste that are coming off of a sea cage. That's where the concept is. Very leaky system in the ocean. Because not only do you have currents, you have tides. Currents don't always go the same direction. Even if you're in an area that has a predominant current, the tides affect it, and the currents actually will rotate in circles around the system due to the tides. So it's a very leaky system in the open ocean, which is why we went to land-based systems. So this is a schematic of our system, and there's a lot of components that we're integrating in. That's why it looks complex. But if we look at the fundamental system itself, I think there's a laser. Yeah, the fundamental system is this recirculating system that I've already talked about. So fish filtration, this is solids filtration and biofiltration. So back and forth in this circle is that basic biofilter that I talked about. And then we run other loops off of that, specifically choosing the water quality that we need for a particular component. For instance, if the assimilative culture is our sea vegetables and our seaweed, the water goes through that and then back to the filter, but we can draw off of this component which has had nitrogenous waste reduced. So if we have a species we're growing that is sensitive to the nitrogenous waste, we can pull the water there and grow that species within the system. So it has advantages in that route. We originally looked at doing just a circular type of system. The problem is that every component then has to be able to handle all of the water in the system. All of the water that's going to the fish, which is a large quantity. The fish tanks turn over 1.5 times per hour. You're pumping, or 2 times per hour if you're going to higher densities. You're pumping a lot of water, and if you're trying to run that through some of these other components, it gets very problematic. So because of the difference in the amount of water flow among components, by breaking it into loops like this, now we can control the water flow, we can control how well the system is operating based on that. So it gets complex in design. It's actually simple when you go out and look at it. Remember this complex design when we go on a tour. You're going to see the system, and all of these lines basically are represented by pipes in the system, moving water from one area to another. But we can have multiple species. Our system has shrimp and fish, and we've had oysters and clams and sea cucumbers and sea urchins and multiple species of seaweed and the sea vegetables, etc., and even microalgae. So that's the concept. One of the things that we do in our studies of this system is look at how do we integrate new species into the system. This is a big portion of, because we want integration of new species for us is turning another waste into a resource. So we look at, okay, we have this waste, what can we grow? What can we do with this waste? What biotransformation can we apply? And sea vegetables became one of the things that we became interested in very early. We were seeing work that was being done at Moat that Kevin was doing about the same time as we were incorporating sea vegetables into our system. And our initial species we started working with is this species here, which is Salicornia, the Salicornia. I think I have a slide that talks about that in a little bit. But that was the initial forays into the sea vegetable world for us, and integrating that. So if we look at the system, I want to look at the system in another way. I want to look at the system in the concept of nutrient flow within the system. So the basis for me, being a fish guy, I'm always fish-centric. Dennis or Megan with their plants would be more plant-centric. So I'm going to give you the fish-centric view of the IMTA. We have feed. Our system being an experimental system, we have a set feed rate for the system. We try to achieve this feed rate every day. We feed 5.4 kilos of feed per day to a tank of fish. In this case, I'm showing you a pompano. The fish consume that feed. They produce the feces and the nitrogenous waste. The uneaten feces in the fermentation, et cetera, is releasing more ammonia and nitrogenous waste into this system as it breaks down a bit before it's harvested. And then those components go to your plants, be that the sea vegetables or the seaweeds, providing the nutrients that those plants need in order to grow. That's the basis of nutrient flow within the system. Productivity in that system, this is some data from Dennis in the early parts of the year. So it's not an even amount every day. Of course, it changes with the seasons. But on the average, we get about 26.7 grams of dry weight per square meter of the seaweed per day, the ova. The fish are fed that 5.4 kilos of feed, about 12 pounds of feed per day. It's a 45% protein feed. We can calculate how much nitrogen that would theoretically produce, and that is then being converted into this vegetable matter in the system. Our whole system has got a surface area of about 67 square meters where we grow plants. Do the math, and you come up with about 1,400 pounds of dry plant material per year in the system. So, and that's off of one tank of fish. It's a 12-foot diameter tank that we maintain at about 30 kilos per cubic meter of fish. I forgot to do the conversion of that, but it's fairly dense. It's not as dense as tilapia numbers for the tilapia producers. It's about a third of the tilapia numbers, but with marine fish, marine fish don't tend to be able to hit tilapia numbers. Tilapia producers are pushing 100 or 130 kilos per cubic meter in their systems. Some of them are even pushing nowadays up to 200 or so, right?
We're not quite that dense, yeah.
But some tilapia producers they're claiming those numbers.
Yeah.
I've not seen them myself,
You're right
but
in the line at that point
yeah. But I've seen pictures of tilapia tanks where you could almost literally walk across the tilapia. They're so dense in the system. So water, I promised you water conservation. So some more data from our system, water conservation. Remember, the standard system is about 5 to 10% makeup per day. The IMTA, and I check this about annually, I look at it, runs at about 0.5% makeup per day. This 0.5%, we measure all rainfall, so you'll see all of our plants are outdoors. They act as catchments for the rainfall, and we measure the rainfall and incorporate that number into this 5% per day. So the 5% is the freshwater, saltwater, and rainfall that go into the system. So a tenfold decrease in water requirements just by adopting the IMTA concept in the recirculating system. That in and of itself is an amazing reason to incorporate integrated multi-trophic aquaculture into most any recirculating system. So what are some of the potential products that come out of the system? Once again, I'm fish centric. I'm going to show the fish first, right? But I will show the plants. So we have grown pompano, cobia, and red drum in the system. All of them work well in a tank system. Red drum especially love crowded conditions. But depending on where you are in the country, you could incorporate other species, even salmon, if you're in an area that's cold, or in Homestead, Florida, I suppose. There's a salmon operation down in Homestead now, amazingly enough. But you choose the species that is most appropriate for your prevailing conditions. That way you don't have to heat or cool water too much. We're growing shrimp in the system. They could be grown for either food or the bait markets. There are two predominant types of shrimp culture systems: clean water systems and biofloc systems. We chose to use the hard stuff and went to biofloc systems. So you'll see our biofloc shrimp tank there. And we've grown, geez, I don't know, maybe 9 or 10 crops by now, Richard?
Twice.
Yeah. Twice that? Yeah, and the shrimp, we always grow them to like like a jumbo, ultra, big, huge guy like that. And they're delicious. Very, very nice coming out of the system. One of the problems with the research system that I didn't mention for fish is oftentimes you have off flavor. Some of the bacteria produce these compounds, geosmin and methyl isoborneol, that cause off flavor. And we have never had a crop come from our system that was off flavor. Here's some of the other products we've done: urchins, cucumbers, sea cucumber, shrimps, conch. We're starting to work a little bit with annelid worms as bait. We've done amphipods as feed for aquarium systems, oysters, clams, and Shirley. This is Shirley right there, Shirley sponges. She works a lot with sponge technology and incorporating. That's probably the most difficult part of the system, is incorporating sponges, but we have a lot of hope. You can talk to Shirley at some point about the uses of sponges. They're many and varied. Now we go to the plants. So remember, assimilative culture, primarily removal of nitrogen and phosphorus. Dennis has looked at the ova and many different other species of plants, including Gracilaria, hydropuntia, which are these red colored algae. If you're in a cold water area, you could do porphyra. You're familiar with that. That's the purple wrapper on your sushi. You can make a green wrapper for your sushi with ova. We've done microalgae for feeding as a supplemental feed for the clams and oysters, and then our sea vegetables, or as I call them, other macrophytes. Not to diminish them, sea vegetables are extremely important in the system, but we've worked with Salicornia here, Cestuvium, which is a sea purslane, Batis, which is the saltwort. I'm trying to remember all the common names Megan's using so that and then we have our sea blight, which is an unfortunate name, but this stuff really tastes great. I think this is the best tasting of the group. But anyway, be that as it may, you can see we've really expanded our species and use, and we've got plans for other species we want to incorporate the system in the future. What did I forget, Richard?
Not that they're edible, but we also grow mangroves.
Oh, we also grow mangroves, the restoration people. We've produced, I don't know, 5 or 6 crops of upwards of 2,000 mangroves in a 10-foot long raceway. And some of those mangroves are now in restoration in the Bahamas, up in New Smyrna Beach. I think Vince have you received some of those, Vince? Yeah. So we're producing them, and they are out in the wild at this point. So the ultimate at the end is what Megan's going to be talking to you about, is the culinary aspect. So this is actually a dinner that I made for my aunt, came up from Miami, and we had just harvested pompano from the system, and we had our Salicornia already. And this is a seaweed salad made with the ova from our system. So it's got seaweed, the ova, grated carrots. It's got sesame oil and some garlic, and oh man, it was wonderful. It was actually better the second day after it all got to meld together. But this is just simple sauteed with garlic and olive oil. So that's what I've got for you. And any questions anybody has, we've got time for it.
Yeah, about 5 minutes.
So I've got Shirley's
Okay,
Sue.
I have 2 questions. Those big shrimp, can you buy them and where?
Not from us. We do experimental, so we produce it just enough to make all of our staff happy.
All right.
So what I'm going to caution you is, remember, this is a saltwater system. So there's not only the difficulty of extracting those in a form that can be used, but you have to do it in a way that removes the salt, because most of the plants that home gardeners use are going to be saltwater plants, which is why we look at these particular sea vegetables, because they are in a group of plants we call halophytes, which are salt-loving plants. And they can live in salt water that's upwards of 50 parts per thousand, which is almost twice, 1 3/4 times seawater salinity. So They can live at low, most of them can live at low salinities, down to freshwater, most of them, all the way up to very high salinities.
Hey, Paul, could I just chime in?
Sure.
So, yeah, I think you can use the nutrients, for anything. But I think what's cool is to instead make that into much needed animal protein. I think it's, the value is so much more worthwhile, both economically, but also kind of from, I don't know, just what does the world need? I think, yeah, we need more protein. And this is a really good way to convert that raw material, because that's what the plants do, get it either to something that can be eaten that way or fed to an animal.
And I didn't highlight it much, but one of the things we look at is, especially with the seaweeds, is how we can use those as feeds for other things in the system. So the sea urchins love the seaweed. So when you look at a crop of seaweed, there's going to be portions that are suitable for human consumption, but the bulk of it is probably going to be at a grade that's more appropriate for animal feeds and that sort of thing. So the grade A would go to human crop, and the grade B would go to animal fodder. Probably one more question.
Thanks, Dr. My first one was the feed that comes in and the source, and I guess it would be different depending on what you're growing, the source of fish. But that would also influence the need as far as what's in it. And then also energy, as they're running the pumps. And is there any, probably use some of the rates of that. Or
Okay.
solar, wind.
So the question was I'm going to break it down into one question. And what are the efficiencies of the sources of inputs, being the feed and the energy to the system? So the feeds are standard off-the-shelf feeds that we use, that fish farmers are using. Fundamentally, those feeds nowadays use very little fish from the ocean. They've much less than they used to in the past. Most of those feeds, the feed companies are trying to get down to less than 5% of the feed, the protein in the feed coming from wild harvested sources. And we've submitted a paper with pompano, which is a very carnivorous fish, where we grew them as well on a feed that had no protein from fish and no fish oils as well from the wild harvested, and they did as well on those diets as they did on diets with the fish protein. And then the second part of your question is alternative energy. We use alternative energy in the system. When you go out there, you'll see we have a 30 kilowatt solar array, which provides the majority of the energy to run the system. And if you were in an area that had good wind, you could have windmills. So these are concepts that we are very attuned to in the system, using high efficiency pumping and alternative energies. Now I'm going to help get Megan's talk set up real quick.
You'll get a chance to ask Paul some more questions on the sheriff, who can take you into the IMTA system. Thank you very much, Paul.
Oh yeah, make sure you ask me all the tough questions.